Okay, so today we're going to continue talking about some of the dynamical systems that Joel introduced last time. So we saw that a lot of the systems around us, from systems in economy to biology to how the solar system works, populations, how they grow, how cells in our body sort of work together and develop, that's all related, and they are all related by this field of dynamics, of systems that change over time. And so understanding the behaviors of these systems and how they work and how we can predict where the system will be in the future is a big part of the mathematics of the last century. And it's also quite a fascinating topic, this question of randomness versus predictability. Because for a long time in science, there was this Newtonian view that if systems are governed by simple rules, and if the rules are sufficiently simple, all the outcomes are predictable. And so with sufficient knowledge of initial conditions and with sufficient knowledge of the rules of the system, and with sufficient computational power, we can sort of predict where the system will be at any future time. And we can manipulate the system in a very easy way. However, more and more we're starting to realize that this view that the nature around us and the world around us is predictable that world is dead, and we can have very, very simple systems with very simple and elegant rules that turn out that they display this chaotic behavior, where if you start from initial conditions that are sufficiently different, you get completely different outcomes and completely different behavior of the system, which makes prediction quite impossible. So last time we saw that, and we talked about two main types of dynamical systems. We talked about different continuous time systems and discrete time systems, and I'm going to go a little bit more into the characteristics of each and when they are equivalent and when they are not towards the end of the lecture. For the first part of the lecture, though, we will be focusing on continuous time systems and trying to understand linear and some non-linear systems that are very well behaved. So for this class should almost nod along in complexity theory, because what we're going to talk about today is systems that are quite easy and nice and good to us. They behave very well. But towards the end of the class, we will see some departure from that behavior, and I think we believe that it's important for us to talk about the very simple behavior, and it could also be very simple for some of you who already took dynamical systems. It's important to talk about these behaviors in order for us to really be able to contrast further in the class when we see the more complicated behaviors, and when we see departures from and when we see randomness and unpredictability. It's important for us to have sort of this base where we go back and try to understand the differences. So let's start with first order systems. So let's have a very simple system, simple one-dimensional linear system. So let's say f of x, where f is a linear function. So a general system like that would be that's not one-dimensional would be xi bar equals fi of x1 xn. That's our general system. And so we can have linear systems again and nonlinear systems. And Joel went a little bit into what makes what constitutes a linear and nonlinear system. And I wanted just to briefly point out first that linear systems are sometimes so much easier to control. A lot of our inability to control systems comes from nonlinearity, and that is because linear systems, when we analyze them, can be broken into parts, and then these parts can be then put together and recombined in order for us to get the solution of the system. So you could almost say that linear systems are equal to the sum of their parts, whereas that thing does not happen for nonlinear systems. When we have nonlinearity, when we have interactions of terms, when we have more complicated functions of the variables, all these make the system behave in a way that a lot of the times we can't predict. So it's these interactions that are interesting. But for now, let's go back to our one-dimensional linear system. And I want to introduce a few little tricks that will help us understand the behavior of the system without getting its analytic form. In fact, I think in most of the equations that we're going to talk about today, we could very easily solve them and get the analytic form. But I'm going to give you a few tricks because to sort of visualize and understand their behavior without recurring to the analytic form, because a lot of the times we can't solve them analytically. And so it's important to sort of get as many properties of these function, of the solution to this equation as possible without being able to solve it analytically. So we will make what is called a phase portrait. So if we have x here, x bar here, let's say our function f looks like this. This is our function f. And so a phase portrait means that, for example, if we look at the points here, these are points where x prime equals 0. So these points, can anyone tell me what happens to the system when we are in these points? So if we start here, for example, what happens here? We stay here, right? There's no movement. If you start at that point, you stay at that point, right? Because here, so these are called, this is what's called equilibria points.
Does everybody understand this notation, x with a dot above it? Maybe you should go through what that means.
That's just the derivative.
The time derivative.
The time derivative. So I will probably switch a lot between these notations.
You're assuming time is the independent variable, basically?
Yeah. So if we start here, we stay here. In general, in order to understand behavior, we sort of try to look in this is a phase portrait. And this line will be called a vector field. So stagnation points here are called fixed points. Now, what happens in between fixed points? What would happen? So, if we see here a positive derivative, that means that the system is sort of flowing this way. When f of x is negative here, x bar is negative, then the system is going this way. So we sort of can map the flow of the system based on the sign of f of x, or if it's under the x-axis or above the x-axis. And so we can sort of visualize the behavior of the system by thinking, if we place a particle somewhere on this x-axis, we're in one dimension. What happens? We can understand a lot of things from understanding what happens to that particle and where does that particle flow in this line. So for example, if we start the system here, we stay here. If we start the system here a little bit close to it, but not quite on it, where does it go? The system goes back. We can sort of, using this vector field, we can trace the dynamics to see that the system goes back to this point. And so...
So Oana, does everybody understand why the arrows are going in the directions they're going in?
It's kind of a convention, right?
So it has to do with the curve she's drawn up there. Maybe you can take a step back and go through that again.
Oh.
How you get the different directions of the arrows.
So let's say we have this type of thing. Does everyone understand why if we start here, we stay here? Is that? So.
Because the
if-
derivative
you
is
know,
0, so there's no change.
There's no change in the system. However, you can also think of it, if you think of it, I've never really thought about it that way, but if you think of it as physics and x prime being speed almost. If you have this on top, if x prime is here, you sort of gain momentum this way, and if you have a negative speed, this slows you down, and you don't go this way. So if the flow, let's say this way, if you have a negative speed this way, it sort of slows you down and wants to pull you in the opposite direction.
Wait, at the 0 point, there's a speed of 0.
So you stay there.
So at the place the arrow is going to the left, it's not slowing you down, it's speeding you up toward negative.
It's speeding you up. So it's slowing you down in the sense of this direction, but it's speeding you up in the opposite direction. Yes, it's like a negative speed in the opposite direction. Sorry?
What are the axes in the example?
You can sit there. I'll grab it from you.
So the axes are x and x prime. So is everyone on the same page? So now looking at these arrows, we can also, these, as I mentioned, these are called equilibria points. We can also see that there are two types of equilibria points. And in a lot of books, you see the equilibria sort of shown to you in this little drawing where if we put a ball on the surface here, this is a stable equilibria, because if you start a little bit next to it, the ball just stays here, and the ball just goes basically back to the stable point. Whereas if you move the ball a little bit to the right or to the left of the surface, the ball rolls away, and this is called an unstable equilibrium. So we can do the exact same thing here, and the arrows really guide us to see what the flow of this motion is. So for example, this point here, if the this equilibrium point, we see the arrows point towards it. So if you start a little bit next to it, you go back to it. You always go back to it from both of these directions. So we'll call this a stable equilibrium. Whereas if we look at this point, the arrows always point outwards. So if you start a little bit next to this point, you'll always move away from it. So any oscillation around the equilibria will increase here, whereas any oscillation around the equilibria will dampen here.
Would it, in the unstable one, would it increase the oscillations, or would it just immediately like take it away?
It goes to the stable one, no oscillation. Any difference from that x point pushes you to one of the stable equilibriums.
So if you start a little bit here, then imagine this particle flowing as like based on these arrows, and exactly if you start here, you're pushed towards the stable point, and then you stay here.
Oh, okay. I was confused because I thought you said it increased the oscillations, like if they would get bigger. But I thought once it goes off that point, it would
increases-
just like shoot away from that
It
point.
increases sort of, if you start next to it, it increases the distance from it.
Okay.
It's not an oscillation in the sense that it's periodic or anything. It just increases, you move further away from it. So let's do an example together and see for an exact function. Let's say if we have x prime x second minus 2, x to the power 2 minus 1. Can you guys sort of do it on your own. I'm going to give you like a minute, and then we'll try to do it together and see if we can determine the equilibria of these systems and whether they're stable or unstable. So we would first start by looking at the face portrait. And so we have x and x prime. What does my function look like? That goes through okay. So these are my two stable points, right? Can anyone tell me which one's stable and which one is unstable?
The first stable and the second stable.
Okay, so we sort of we determine the vector field, right?
If it goes in the other way, because
Mhm.
it's negative right there. Yeah.
This one?
Then that should be pointing outward. But should the first one be pointing that way because it's positive? That you're in the graph.
So if the area is positive, it flows this way, right? If the area is negative, it flows this way.
Yeah, but your first
Just
arrow's
the
going
the
in
left
the-
arrow is it's unclear which direction.
Oh, yeah, sorry. I got confused for a second. Good job, though. So this equilibria is,
Unstable.
and this equilibria is. We generally denote unstable equilibria by open circles and stable by by full circles. So for example, now if we look at the logistic equation that we talked about last time. And try to do the same thing. So our logistic equation was nRn1 minus n over k, right? So if we were to plot this one, it only makes sense to plot it for positive n. This sort of looks also, it's a parabola, so it's like this. And so this is k over 2, this is k, this is 0. Can someone tell me again what the stable and unstable equilibria are? Unstable. Okay. So what do we know about this system now? So we know it's equilibria. We know if they're stable or unstable. It would be very easy to solve it. But let's see if we can sort of plot, if we were to plot how the system behaves over time, just using this graph. Can we sort of do it qualitatively? And I think we can do it because we know a lot about the system. We know that if the system starts somewhere near 0, it goes to its carrying capacity. We know that if it starts above the carrying capacity, it then equilibrates itself again to the carrying capacity. We know that there is some sort of change happening here at k over 2 because whereas the slope, the concave versus convex type of the slope shows us if the speed is gaining momentum, if it increases speed or it decreases speed. So let's say if we plot n on the x-axis, time on the x-axis, n on the y-axis, this is k. If we plot k over 2, we know that k is a stable equilibrium point. And so if we start above k. This sort of tells us that there is this pull back to k. And sort of this is qualitatively how the graph of this function n will look like. If we start here, somewhere near 0, we get pulled up, and then we slowly, with a high speed, and then we slowly converge to k also. If we start above k over 2, we also go up, but our speed is slower. So without solving anything about this equation, without any analytic, just doing the simple phase plane graph and looking at sort of the flow on the x-axis, we can sort of get a lot of information about what we expect this system to do. And this is a very simple system. We could have done it analytically, but this is just to show you different tricks that we can try for systems that we don't know how to solve.
I have a question.
Mm-hmm.
It seems now we're talking about nonlinear systems, but then logistic equations nonlinear.
Yeah, this is a nonlinear.
And then I guess
It's still one-dimensional and very well behaved, though. Yeah.
I guess this is a sort of perturbation analysis. I mean, if you're very far away from k, how do you know it's gonna? I mean, that it's gonna go back to the stable equilibrium.
So this was just very qualitatively. I'm gonna now quantify the stability. I'm gonna go back and tell you, okay, it's stable. How stable is it in the sense how fast am I moving towards the equilibrium? Is that sort of answering your question?
Well, I guess, I mean, in a nonlinear system, if you're very far away from k, or you're very far away from a stable equilibrium, it's not clear that you're going to go back to the
So
stable.
you're gonna go back. That's also possible. I don't think it happens for this system though.
Okay.
I think for this system, you always go back to k.
Okay.
But I agree, there are systems where you could, if you start very far away,
You saw it with your previous one, with a sort of sinusoid. If you started far away from one equilibria, you'd in fact get moved to another equilibria, or if it was unstable, you just move all the way forever.
You can just wander.
so that's, well,
But
for
the graph
one-dimensional
of the
systems.
phase diagram shows it to you.
So for one-dimensional systems, you can get all the information on a phase diagram because phase diagram tells you the equilibria, and if you don't move away from the equilibria, you just go to infinity or minus infinity. But you always say they're very well behaved in that sense because it's one-dimensional. You always stay on this line, and this vector field tells you exactly where you're going, no matter what point you start from. So even if you don't go towards the equilibria, then you just there's like exponential. If you didn't have this, the second term, the nonlinear term, you would just grow exponentially, right?
Couldn't you have like a periodic orbit or something?
You don't have
Not-
inertia in this
Not in-
equation.
Not
Okay,
one-dimensional.
understand.
Unless
Yeah.
the space is circular. If it's not a line, if the space is a circle, you can have a one-dimensional circle.
But if I
That can be
change,
periodic.
if I change that equation to put in a term having to do with x minus 2 and something like that, then I put in effectively an inertia term, which you don't have. And then you could get periodic movement.
Do you mean instead of f of x or?
Somehow f of x doesn't just depend on x, but it depends on x of t minus 1, things like that.
It'll be a two-dimensional system. It won't be one-dimensional.
So for
Because
example,
t
if you
minus
have
1 is the second dimension.
To get oscillation, you have to have two dimensions.
Yeah, I agree. Yeah, because
So-
you have to pass through an equilibrium.
Yeah. If you had oscillations on a line, it means at one point on that line you'd be going in one direction,
Right.
and then you'd come back to the same point and be going in a different direction.
Right, and
Which
if I
is-
have a ball with inertia in a one-dimensional system, that can occur.
But there's two dimensions because you have momentum.
Momentum is a second dimension.
It's a state.
Fine.
Yeah, you have the state of your location, and you had.
So that would
In phase
basically
space.
be, you could still, I mean, it's still, this is two-dimension, and I'll tell you why, because that would be something like this, f of x and x prime. Let's say it's just f of x, just to simplify. this,
Yeah,
then
that will
this
work.
we transform into x. So we transform into two-dimensional systems by doing this, by putting x squared equals x prime, and then fx squared, oh, how do we do this? So u y equals f of x y prime equals f of x and y equals x. So basically you get x squared equals f of x squared equals y prime, so y prime equals squared plus y equals x prime. So basically, any higher, if you have any higher derivatives here, you can always transform a higher derivative one-dimensional system, sort of, that's always equivalent to, it's actually a multi-dimensional system. Because you can put y equals x prime and y prime, which is x double derivative equals f of x, and this is a second derivative system.
So everybody
So now
was
we
saying the
don't-
same thing. So you were saying two
Yeah.
dimensions, you were
Yeah.
saying x squared term, you're both equivalent, depending on how you
Right.
think about the system. The important part is you need a second derivative.
Yeah.
Maybe it's good to
And
clear.
any other, if you have an nth derivative here, you can always transform this to be in this way, to be an nth dimensional system. But now we're going to talk about two-dimensional systems in a bit, but let's just, very simple one dimension.
It's
But
also
that's a
easy,
good
it's
question.
easy to get confused on what dimension means. It doesn't mean motion in one-dimensional space or motion in two-dimensional space. The dimension is how many pieces of information do you need to represent the system at any time. That's one way to think about it.
Also, you did something like that in the readings, I think, right?
So, if we want to quantify a little bit better what stability means, so we want to quantify the sort of rate of decay to a fixed point. So in order to do that, let's say we have, this is our fixed point. And let's say we have eta is a small perturbation around it. Around the fixed point. So then let's try to see what the derivative is. So this is d dt. This is just the derivative of x, because this is a constant. This is then f of x. If we apply a Taylor expansion around the fixed point, we can say it's f of x squared, f of x fixed point, plus beta f derivative at the fixed point, plus higher order terms. It
Oana,
can be, yeah.
could you explain what a perturbation is and Taylor expansion is?
So basically, the Taylor expansion, let's say Taylor expansion around a certain point x0 for a function that behaves pretty well. It's pretty well behaved. You can write it as
Is there a division by the
Oh.
colors and stuff?
There's no half. Half's not
no,
extent.
that's 1/1 factorial here.
So for people who haven't seen Taylor expansions, it's just a fancy way of writing an approximation. So that's approximately equal to the function. And you're writing it as a polynomial, which is why it's useful. Sine functions are hard to deal with, polynomials are easy.
So you're basically sort of almost linearizing this function around that point. If you ignore these second order terms, it's basically, this is a linear function around this point,
Right.
plus a constant.
You said if it's nice. Can you give me a little bit the definition of niceness, because
Right,
a lot
so
of
it's definitely
input-
true, well, the functions, first of all, need to be derivable, right?
Okay.
So I don't really remember that, if you look up Taylor expansion,
Okay.
they're exact, sort of very clear when you can apply Taylor expansions. But if continuous, definitely, continuous and derivable
That's
up
nice.
to a certain, that's nice, yes.
Okay.
It's pretty smooth.
And when do the second terms become big, when do I know the second term and all those aren't too big that I can't just throw them away?
So that's
that the
something
same
tricky,
thing?
that's a good question. It's very hard to know when to stop
Oh,
adding terms here,
okay.
like what the error terms are. Here, your error term would be, so you'll multiply, for the second part, you multiply by x minus x star squared. So if you believe, so let's say if you assume that you start near enough the equilibrium point, so you have this small perturbation, such that you assume that you can ignore the second order terms, then, which is what we assume here, if, and that's a fair assumption, and you can read more about it in the book, provided that this is different than 0. If we have this different than 0, so f derivative at the fixed point is different than 0, us ignoring the second order terms here is a fair assumption to make. And then we are left with the fact that, I'll write here, so this tells us that, this is very similar to something that we saw last time. It tells us that if this term is, let's say, smaller than 0, what happens to this perturbation over time?
Can you say that again?
What happens to the perturbation? What happens to eta over time if we assume this is smaller than 0? It decays, right? It grows smaller. It goes to 0. What happens if we assume that this term is larger than 0?
It goes to infinity.
It goes to infinity. This is exactly
Larger than-
what one of the functions we saw last time.
So this perturbation, just in case anybody's unclear, like imagine you have a pendulum or something, and you just sort of move it like a slight little bit away from the equilibrium point. It's going to move back towards the equilibrium point, and this is telling you exactly how fast that moves. So this eta thing is just the distance you are from the equilibrium point. And so if it's decaying, that means you're getting closer and closer to the equilibrium point, and if it's growing, it's going to infinity, that means you're getting farther and farther away. Just like we talked about with the stable and unstable points.
So going back again to this example where we have this ball sitting on top of a little cliff. A perturbation basically means moving the ball a little bit this way. This is an unstable equilibrium. If we move the ball a little bit this way, it falls down. Here, this stable equilibria, here, eta will, it can be proven that this is sort of smaller than, this will stay here. Any perturbation, if I move the ball a little bit in these ridges, they'll eventually just come back down. Like if I move the ball a little bit upwards this way, the ball will always come down. But here, if it's right on top of this cliff, if I move the ball a little bit, it'll just fall down the cliff. And this is what this eta, this is what this is measured by. The sign of this function and how, and the value of this function measures in a quantitative way how this rate of moving away or coming towards the fixed point. So then if we go back to that graph over here, this is our function, this is our function f here, right? So we see here that at the fixed point, the slope of this function what is the slope of this function at this point? It's negative. So that's why, so if it's negative, what does this say about the k here, the stable point? If we have negative here, that means it decays, right? So then that's why we go back to why did we put the arrows this way? Here, the slope of this function is negative here. So positive here, the arrow goes this way. Negative here, the arrow goes this way. So we see again that we can tell a lot about what the slope of this function is, or if it's positive, if this function is positive or negative at the fixed point.
So the terminology we use is that the equilibrium point decays, or the fixed point decays.
Stable. Stable means decay of
So the perturbation
perturbation.
decays.
Yes, stable means decay of perturbation. Unstable means perturbation gets larger, and you just move away.
And notice that you guys already know all of this stuff. So she's just presenting in a different way. And if you took calculus, which you all did, you told me, you learned that if the first derivative is negative, then that means something about the stability. In fact, that means this is stable. You really learned if the second derivative is negative, that means it's a stable point. And that's exactly what you have here, because you have two derivatives. You have a time derivative and you have a derivative in your f function. So maybe you don't see the connection immediately, but it's really two sides of the same coin. There's nothing new.
So another interesting question is what happens if now you have this to be 0? And let's do some exercises together. So for example, if we have this function, can someone come and help me do the vector field here for this function?
It's just
Do you want to do it?
no. I mean, it's just an upside down graph.
Okay. It's x to the third though.
So
Maybe
it's
maybe this would be a good chance for people to work in groups and try to figure this out. And maybe
Oh, so yeah,
groups of
it's like
two.
that. Yeah, I'm sorry. Yeah.
Wait, do you just want it like mapped like the other one?
I just wanted to do the same thing that we did for this one. Do you want to do it?
I'll do it.
Sure.
Yeah.
Oh, think you're closer. You'll have to come up with
Here,
this
you can do this one and I'll give you another one if it comes through.
So I think x cubed is like this with negative, so it's like this.
You can do this one.
You can do it behind me, there's another book.
You didn't put any arrows. You don't go up and down. This is your
Oh, I
axis.
see. Very good.
Is that all you want?
Yep, that's awesome. So actually for both of these functions, we have, it turns out that we have f derivative at this equilibrium point to be 0, but they exhibit very different behavior in terms of stability. And if we look at something else like, for example, if we look at the function can someone tell me x equals 0 if it's stable or unstable? So where do I put the arrow here? Where do I put the arrow here? So this is like a point where it's stable on this side, but it's unstable on that side. So if you perturb it a little bit in this direction, you go back to 0. But as soon as you go, if you go positive, you perturb it a little bit away from 0 here, you move further away from 0.
Just to clarify, if it started on the negative side of the axis and you perturbed it in the direction of 0, it would then
You
stop at 0.
Anywhere you start here,
Mhm.
if you perturb it away from 0 this way,
Mhm.
you go back to 0. But anywhere you start, you just go to 0 in here.
Okay. And
If
then
you
stop.
perturb it a little bit in the positive direction, you just go away. 0. So as you see, these are very equilibria of a system and sort of this flow. What does the system do over time? These are very simple tricks that allow us to really predict what the system does over time. Where will it be? As we saw here for the logistic equation, we didn't solve anything, and we were able to predict over time sort of what is the qualitative behavior of this population. So we see these dynamics. This is like very simple, linear, a little bit of nonlinear, dimensional systems. And it's interesting, but it's not that interesting. They're very predictable. You can either go to these fixation points or you can go to plus and minus infinity. So what's interesting about them? And there are some cool stuff about them that have to do with certain dependence of parameters. The fact that this flow that we see here and how this behavior, how the system behaves depends a lot on certain values of the parameters. So let me give you an example. Let's say we have this system now. Can someone come and do the same thing that we did for the system? Is it M? That's an R. This is a parameter R. So do the exact same thing that we did here. Do the
Yeah, but what
sort of.
what is the parameter R?
Oh, R is a constant parameter. Yeah. That we don't know.
Can I assume that it's positive or negative? I just want to know.
That's a really good question. So let's do it both for positive and for negative.
So, okay, like that? Is that right?
Yeah, let's do it two separate graphs.
Oh, sure. Oh, I just drew the same thing. Excuse me. And we're still interested in when it's 0, right?
Mhm.
So this would be this way, and
Mhm. What about here?
There
Well,
is
is it positive or negative?
oh, but it doesn't ever.
I know you can still put the vector lines though.
Okay, even though
It doesn't cross.
it doesn't get to 0.
The flow is the same. The flow of the system is the same even though we have no fixed point.
Okay, so it's kind of always.
That way. Awesome. Thank you. So this happens for r bigger than 0. This happens r smaller than 0. And then we can sort of do something like this. I equals to 0. Right? So now we see that as we change this parameter r, starting with, for example, if we start with r smaller than 0, we have these two stable points. And these stable points, one of them is stable, one of them is unstable. As we sort of move r on the r from negative to positive, so we move r this way, that sort of the stable point sort of moves towards 0 and they sort of shrink, come closer and closer together until we reach a positive R, and then we have no equilibrium points and the system will just move towards infinity. So we see these are called bifurcations of the system. So based on the parameter, we see this movement in how many stability points there are. And there are also situations in which a fixed point must always exist, but then its stability changes based on different parameters. So going back to a normal form of that equation, logistic map, let's say we write, this is the decay rate R, x minus x squared. If we do the same 3 graphs for this function, so this is R bigger than 0, this is R equals to 0, and this is R smaller than 0. I'm going to quickly draw these. So here, x equals 0 is always an equilibrium point for the system. Yet the stability of this equilibrium point can change according to the parameter R. It can go from being a stable equilibrium point to being sort of a mixed stable and unstable point to being unstable. So we see that sort of these bifurcations, depending on parameters, we can have either creation and destruction of equilibria for our systems, or sort of changes in the stability of that equilibria. Any questions so far? Do you guys sort of see why these types of mappings are important for us to understand? Okay. Now let's move to two-dimensional systems.
Oana, could you give a physical example of a system that has a parameter that you change and like what that would mean in terms of a model?
So I'm going to close the class with that.
Okay.
But I mean, even for I think this last example that we talked about, that's sort of an equivalent of the logistic map. So we saw that it all depended on the R parameter. So if going back to, let's say, sort of if this parameter was positive or negative or 0, basically meant if you have a positive sort of growth rate or a negative growth rate. So the R parameter here just represented the growth rate, and so it sort of showed what the system did based on the growth rate.
Can I say one more thing about that?
Yeah.
So when I was talking about the logistic equation, the R parameter was this thing that we got from all this microscopic complications that we didn't know about. And then the X thing that we're looking at was the sort of macroscopic behavior of the entire population. So this is telling you that if you change the microscopic details, and that's effectively changing R, the stability analysis tells you that you can get qualitatively different behaviors where when your fixed points change stability, when you go through one of these bifurcations. And so what you're learning by doing this is how the microscopic details, how they affect the qualitative macroscopic details. And that's really the power of bifurcations and these things. So that's an example of how this all fits in with what we were talking about last time.
So now, if we move to two-dimensional systems, so far our growth was our movement was pretty restricted, right? We could only stay on that axis, and as we saw before, we could only go towards a fixed point or towards infinity or minus infinity. However, if we have a larger number of dimensions, like more behaviors are possible, a wider range of behaviors are possible. So if we only look at linear systems for now, a linear system in multiple dimensions can be written as this, where now x is a vector, let's say 2 dimensions x, y, and A is a matrix. So then we would just get and one of the reasons we call the system linear is because if we have two solutions of the system, x and y, then automatically any linear combination of them is also a solution of the system. Something that we can notice here is that the vector 0 is always a solution of the system.
If you go back to one dimension, it's just A times X, right?
Yes.
And you don't even have a constant term in your either of those. And if you put a constant term in, then it blows linearity. It's not linear
Oh,
anymore.
you can have a constant term.
I don't see it in your matrix equation.
Ax plus b is a linear function.
But
I think you can show that you can always. This is sort of a form. You can always reduce a system to a system with 0 as the solution. So if you added a constant, so
a linear system can be xy, a, b, c, d,
so
xy
you can have ax
plus
plus by plus
k1, k2. And that's still your linear
yeah.
system.
Yeah, but I think you can show that you can reduce any system to this form.
To the non-biased one.
Mm-hmm.
Okay.
And then if you have, and then moreover, don't remember that when you have something like this depends, it depends on the initial conditions, right? So a general solution for this is times a constant, right? Depending, and so based on the initial conditions, that's how you get uniqueness here. So when you integrate, always, like all of these systems, I never mention initial conditions, but you always also set initial, like it depends where you start from, right? When you have differential equations, you also get, you give, where do you start? You give your initial conditions.
In the 1D case, the equation gave the entire behavior of the system whatever the initial condition was.
Yes, but when you solve it, I'm just saying when you solve it analytically, for example, for x prime equals ax, right? When you solve this analytically, what are the functions that have this property? They're c, e, a to the t, right? So c, what is c? C is a constant. Like if you put any constant works here, you get an infinite number of solutions. But your initial conditions, x at time t equals 0 equals x0, sort of gives you what this constant is. But we don't worry about these constants right now.
Sorry.
Mm-hmm. we can again, for these types of systems, do exactly the same thing. We can visualize the solution as trajectories into a phase space, and sort of, this is called sort of phase plane, because we're in two dimensions. And so, for example, let us just take the spring, a mass hanging from a spring example. This is an example that's basically in any book that you look. This is one of the most famous examples. Here, x at time t is where the mass is at moment t. And so you can find that the rule governing the system is this one. So here m, this is for the spring pendulum, but here m and k are basically parameters. One is mass, parameters, fixed parameters, constant over time. So we go back to the same thing. Now we have a second derivative, but we can write the system. This is actually a second dimension system. So we can write this system as this. Right? Where this is again a constant based on the previous constants. Because x derivative equals v, and then v derivative is x second derivative, and then you basically put x second derivative equals minus k over mx, right? So that's how you get sort of this type of second dimensional system. And so let us look now in the phase plane x and v. Okay, we do it here, x and v. What happens? So let's just say we simplify and let's put v equals 0. And then in that case, we have this. So we see that if we are, first of all, the origin here is a fixed point. If you stay here, if you start at the origin, you stay at the origin. If you start here, where do you go? If you start somewhere on the x-axis, where do you go? You get pulled downwards if x is positive, and you get pulled upwards if x is negative, because you have this negative minus w squared term. And this is proportional to how big x is. So for example, the vector space will be smaller here and then sort of increase as x increases. And this is how we know this. And then for example, we can also write for and then what happens here? What happens on the y-axis? Can anyone tell me what happens on the y-axis? So for example, if v is positive, which way do I go on the y-axis?
Well, x dot is positive, so you go that way.
You go that way. And then if it's negative, which way do I go? You go back here. So it turns out that actually the system, this phase space sort of looks, I did a very bad picture of it, but we do a better picture. We actually get something like this. And so finally our system will be made up out of, these are called closed orbits. where on any, if you start, this is our x and b, if you start the system on any point here, you will just go around and then retrace your steps to your initial condition. So you circulate around the closed orbit until you get to your initial condition. And this is very easy to visualize for the pendulum. So for example, if we think of, this is also in your books, if you think of if you think what happens to the pendulum, right? So these movements here, these movements correspond to what the pendulum does in real life. So if you start at 0 and you give it no momentum, you just stay there, right? If you pull it down, what happens? So these circles sort of correspond to what happens to each of the pendulum. So for example, if A corresponds to this position here, B corresponds to this position here, then for example here, A and C, there's no speed, right? The speed is 0, V equals 0. And so these A and C correspond to positions where the pendulum isn't moving, right? Either at the upper edge or at the lower edge, and then the pendulum bounces back.
With no friction in that case, or no
No
dissipation.
friction.
Isn't it a spring different from a pendulum? Because the pendulum.
Oh, sorry, not pendulum, spring. This is a spring, sorry. Yeah. So these are different types of behaviors. We saw these different types of behavior, these closed orbits that now you can have in two-dimensional spaces and you couldn't have in one-dimensional spaces. If we want to draw, let's do an example together. Let's say we have this very, very simple system. Why don't you guys sort of either in groups or alone try to do the phase space for this system?
X dot equals 0?
This is 0, yeah, and y dot equals minus x. Y. You can work together and try to figure it out. I'm going to give you guys a couple minutes.
So, X and Y, right? It's got
Sorry.
I never know when my X's are.
Okay, you win this collaborative.
So, yeah, so I think it's really useful to add variables to the X.
X dot's always zero.
So how are we?
So X, it should be this X.
So the axes are
X or Y?
No, the axes are X and Y.
X is always constant.
So now that's a two-dimensional
So
system.
so that means we're the same thing.
And then you just say like at any point in this space, when this X and Y, how is X changing, how is Y changing?
This will be the same as this, and the same as this, anyway.
So if like I
X
have
doesn't matter.
positive X,
So then we have Y dot equals Y.
Maybe we should call it
so you can sort of break it
X
into
to Y.
how much X changes.
Because there are two dimensions, no?
Yeah.
This dimension is Y.
So we're basically just moving Y, Y down.
Okay, so we gotta have.
And basically,
So like everything is locked in.
if Y is positive, yeah.
I mean, I see what you concluded, but I'm trying to. So
So at this point, I meant a positive one.
It is.
Negative one changes.
If you're
So we're trying to figure out if that could be
So why would it not? So would y becoming more
So
negative in this
it
one
just
too?
tells me that there's a stable line. Yeah, but I'm saying in this whole phase space, it would be instead of stable.
So changing y.
It's becoming less in
Right,
general.
right. You can
not
imagine
just
that.
on
It's approaching zero.
somewhere else.
Okay.
It's becoming less on magnitude.
Okay, so I guess that's alright.
Like this, and
Can we do
be shorter.
Cool.
That's my guess.
Yay.
Yeah, well, so arrows. Carrots are good.
Which says
Oops, I forgot.
one.
Oh, so basically,
Oh, it's already pretty high.
Two slower.
yeah, so basically,
Well, I think.
no matter where you start, you're gonna go to the, you're gonna stay in X, like if you start here, you're just gonna go here. If you start here, you're gonna go here, if you start here, you're gonna
practice on this?
Yeah.
same thing. Because X still is an initial
And y tends to
right, so Y tends to 0, but X just stays where it is.
What's the state?
and x versus y.
Okay, so that's your,
Everywhere, exactly. Beautiful.
So I missed the first step.
so then the first,
Does anyone want to venture?
if you designate y
So what would this parallel
so
look
you
like?
wash that equation out.
You can test this.
Y
She's ready.
You're ready!
I don't know,
Yay!
it's really kind of like a one-dimensional system because X isn't changing.
So I'm not sure the
No
x.
movement,
Like if you dropped the ball
no movement in X.
straight down.
So you
Well, I'm trying to
stable on the entire X-axis.
But all it does is put,
Because then there's
so
a
if you
negative.
start on X, where do you go?
If you start on x, you stay in x.
You stay in X. And if you start with Y0, where do you, like,
Oh,
where
so
Y
you
equals
should
0,
dot.
do you stay there?
If you start at y equals 0, you stay there.
You stay there. So these are always like cross the lines, right? Because these are stable points. These are equilibrium points,
I
sorry.
like the color the whole thing then,
Yeah.
We were thinking that it's really a stable line. I mean, like, X equals 0 is sort of the fixed
Gravity.
or Y equals
Sort of
0.
a trick question.
There's not a fixed point,
Yeah.
it's a
It's the
fixed
center of the sun.
line.
There's every point on
Gravity's
this
all
line,
relative, so
So,
that's not how it
it's
works
actually
in
called
reality.
neutrally stable.
Because you have the
And
gravity
you
of
know why?
the Earth's pulling on the gravity of the moon,
Does-
pulling on the
does
gravity of the
everyone,
sun. A closed system of like two lines, the gravity of one to the other.
Does everyone get, sort of, was everyone paying it, did you all get this result here? So basically, what happens is if you start on X, you stay on the X line, right? And then you see this decay in the Y parameter. So if you start with positive Y, you see this decay towards the X. Towards the X line. So positive Y goes down, negative Y. So basically this line is filled with these points that are, if you start there, you stay there. And it's actually called neutrally stable, and I'll tell you why in a second. If you start, what happens though, this is not quite the same definition of stability that we had before, because let's say we perturb this point. If we perturb this point on this axis, up and down, this point is stable, right? The arrows point towards it. But what happens if we perturb this point a little bit on the x-axis? It doesn't go back, right? It stays there. So that's why this line is called neutrally stable, and you have this neutrally stable axis. Did you guys generally get this? And if you want to read more about these types of different types of stability that you can have for two-dimensional system, you can read more in the Strogat's books or in other books. Look for asymptotic stability and Lyapunov stability and the difference between the two.
You gave two terms, asymptotic,
and Lyapunov stability, if you want to
Which
read
is
more.
what, where? Because you've shown us lots of things. Which is asymptotic?
Right. So this is sort of late. I didn't
Okay,
want to
they
really
don't
go into that.
correlate.
Lyapunov stable,
Okay.
but this is not asymptotically stable. What asymptotic means is that as t goes to infinity, if you start near the solution, you go towards the solution. What Lyapunov stable means is that if you start sufficiently close to the solution, you stay sufficiently close to the solution. This is Lyapunov stable because if you start sufficiently close to the solution, you either go to the solution or stay to the equilibrium or stay sufficiently close. You don't go to it. But if you start within a vicinity, you stay in that vicinity. Whereas asymptotically stable, if you start in a vicinity, you need to go as t goes to infinity to the solution. So that's the difference. But if you guys, these are more complicated, so if you want to read more about it, you definitely look these things up. So this is really a Lyapunov, but it's not asymptotic. Okay, so one thing that I also want to talk about a different type of trajectories that you can get in a two-dimensional space, and this will help. So for example, if we have, back to this system, where x is a vector here, right, and A is a matrix. If we want to search for solutions of the form x of t, e to the lambda tv, and you plug this in, then you get that AV must be equal to lambda v. Does anyone sort of bring back any memories, this form? What do you think of when you see this type of equation? Eigenvalues and eigenvectors, right? So this basically says that lambda must be an eigenvalue for the matrix A, and V its corresponding eigenvector. So then if this tells me that if I have let's say I pick one eigenvalue lambda y, my eigenvalue lambda y will give me, and its corresponding eigenvector will give me a solution to my equation. And not only that, but because it's a two-dimensional system, we have two eigenvalues and two eigenvectors. So if the eigenvalues are different, as I mentioned before, any linear function of my solution will also be a solution of the system. So we find a whole range of possible solutions to the systems just by sort of getting the eigenvalues and the eigenvectors associated with the matrix A. Where here lambda 1 and lambda 2 are the two eigenvalues of the matrix. And there's a lot of theory that we can go into. So for example, what happens when the eigenvalues are equal? When lambda 1 equals lambda 2, it can be proven, and you can read more about it in the book also, that you get what is called a star point. So from every direction, you approach the fixed point. Now, if, for example, the eigenvalues are complex, if you have lambda ij are complex conjugates, then you can get either spirals. So this is your fixed point, and you approach it on a spiral, or you can get centers, as we saw before for the string, where you have all these different trajectories. This is if lambda j are complex conjugates. So there's a lot of mathematical theory concerning that has to do with different properties of the eigenvalues of my initial matrix of the system and what type of trajectories my system can get into. And already we see that we have these much more interesting trajectories that we saw in one dimension. And this is for just 2 dimensions. And I want to just briefly mention nonlinear two-dimensional systems, but we'll talk more about that next time. But briefly mentioning nonlinear systems that behave very well, it is possible to sort of do a similar type of stability. So for nonlinear system, let's say we write y equals gxy, right? It is possible to do a very similar analysis for stability as we did in the one-dimensional case, where f derivative at the equilibrium point gave us the behavior and the stability near the fixed point. And in that case, in this case, it has to do with you need to compute the Jacobian matrix for the system. For x and y at the equilibrium point. So there are nonlinear systems where if you linearize the system in this way, so our new linear system will then be sort of x equals this Jacobian, I'll call it j. Now this is a linear system. We linearized our initial, we call it linearizing our initial system around the equilibrium point, so getting the Jacobian, and this is our linearized system. If our linearized system has equilibria that are sort of stable enough in the sense of spirals or centers, and there's more on this in the book, what type of equilibria should our linear system have in order for this to be true. But if our linear system is sufficiently well behaved, it is generally safe to conclude that the nonlinear terms don't matter. So for nonlinear systems where they are sufficiently well behaved, it is a lot of the times what people do is just linearize the system and assume the nonlinear terms don't matter under certain conditions that you can find more about in the book. And now I want to change gears a little bit. Maybe we should let's take a 5-minute break. In the last part of the class, let's just shift gears a little bit and look, because we only talked about continuous systems. Why only talk about continuous systems? Why not add a little bit of discrete systems in there? So a little bit of difference equations, right? And talk a little bit about, get into what the differences are and why model a system as discrete versus continuous depending on what your initial model is. So one would think sometimes that discrete equations are easier to handle, definitely mathematically, are harder to handle mathematically, because if in a discrete equation you sort of don't flow smoothly anymore. You hop from place to place, from, let's say, generation to generation, if we talk about a biological system. So let us, just a very brief example. Let's say you have the system x at time n+1 equals cosine x of n. It's a nonlinear function, and now this is discrete, right? You have x1, n equals 1, and so forth, x1, x2, and so on. How do we sort of do the same type of tricks? How do we find, sort of, without solving this equation, the same types of behavior? So I'm just going to very quickly show this to you, and then we're going to move on to the logistic map, the discrete version. So this is what your function looks like. This is a diagonal line. This is x of n. This is x of n+1 here. So what we're doing is called a cobweb diagram. And I think cob is spelled with double B. cobwebs though. So let's say we pick a starting point here. If we want to determine, so the stability of the equilibria for this equation turns out to be x equals 0.739 and so on. If you plug in x equals cosine of x. But we want to determine, without knowing this, we want to determine sort of what the system does. So let's say we start at time 0, we start here. We can draw a line upwards. This is our function, right? So at time, if this is time 0, at time 1, we will be here, right? Because here, x1 equals cosine x of 0. Then we can try to find where this is on the x-axis. So now this is our new x1, and we want to find x2. How do we find x2? We trace back to our function. So here, now x2 is again cosine of x1. If my x1 is here, x2 will be here. And then we trace, here I moved in the wrong direction. I should have moved this way, right? So to find my equivalent on the x-axis, I moved to my diagonal to my x equals y function here, right? So if my x2 is here, where's my x2 on the x-axis? If it's here, I trace it back to my x equals y, and I trace my x2 back here. What do I do now? For this x2, where's my x3? I trace back to my cosine function. From the cosine, I trace back here. Then I trace back to my x3. I trace back to my cosine function. And eventually, you'll get something like this. This is a cobweb where, and the equilibrium will be somewhere here. I didn't do a very good drawing, but we'll see a better drawing in a minute. So this is how you do the cobweb. You go back to your x and y function, you retrace, you go back to your initial function, and sort of, if the equilibria is stable, slowly you'll just approach it in this cobweb-like fashion. For example, here, and you can tell this in a very small number of steps because I didn't go x3 immediately came back. If x3 kept going, that would have been a clue to me that this equilibrium is not stable. But x3 sort of came back, and the points on the x-axis sort of will eventually just slowly approach my equilibrium point here. Okay, so we're going to talk about the logistic map in discrete time now and contrast it with the logistic map in continuous time, because it really shows how discrete phenomena can give rise to quite complicated and unpredictable and fascinating behavior from very simple rules. So if you remember the normalized logistic map, it is a nonlinear equation, but it is very, very simple, right? So xn plus 1 equals rxn 1 minus xn. It doesn't take too many characters to write that, yet we will see that the behavior we get is very complex. So this was first written in a paper in, I think, 1976 by Robert May, in which he presented the logistic map in discrete time. It was the first to show the presence of chaotic behavior for it. So to look at, I wanted to write a little bit more, but it's okay. It's fine. So you guys, I want to write the equations though somewhere, so that everyone has it. Sorry, so that Let me remember it. Okay. So I'm just using Wolfram alpha for this. So let's see what happens if our R is pretty small. We give it an R equals 1, an initial condition 0.2, let's say. We can also change the initial condition. And let's see how our system looks like. Why did you not? Okay. So if we look at our system here, we see this decay. We see this decay towards this equilibrium, towards this fixed point. And if we want to look at our cobweb diagram, there's really not much to see here. Let's increase our R now to, let's say, 3. We already see a different fixed point, and now not only is it a smooth behavior towards the fixed point, but you start seeing these oscillations. So because this is a discrete system, sort of ignore the lines between these points. If you ignore the lines, it's just the points that we're interested in, and we start seeing this oscillation around this fixed point. Let's increase R a little bit further again. Let's say to 3.5. If we look at this line again, we can tell that the oscillations are different again, and it's actually a period 4 limit cycle. So every 4 generations, you get to the point that you were before. So it's very easy to see if you guys look at these points over here, down here. Every 4 generations, so this is generation 8, generation 12, generation 16, and so on, generation 20. This point repeats itself every 4 generations. Let's see what happens if we increase now our a little bit further.
Only after a while, right? The first few points.
After the system sort of goes into
So
its routine.
what is it, 20 or 30?
This looks like about 10.
10. Now, is
12.
it exactly the same after 20?
It's exactly the same. After the system sort of gets, it depends on your starting condition, right? 'Cause
But
if
in
you
this
start,
case, it settles down exactly.
it settles down exactly. Yes.
Okay. It's just not
periodic.
asymptotic to 4 different points. In this case.
It's not. Yes, it's 4 different points in this case, and it depends. If I change the initial condition here, let's say I put this. Initially, it will be different, but it settles back into these 4 points again,
Okay.
right? Same R though. This is the limit 4 cycle.
Oh, okay. You just different initial.
Different initial conditions.
Now,
So
if it was-
this part here, if I have different initial conditions, this is a little bit, this part here will change, but eventually the system falls back into its 4 point cycle. Now, I can change the initial condition again, 0.5. Same R, it falls back into the same cycle.
Okay, and if you change the
cycle.
multiplier, the 3.5 to 3.5001,
Let's see what happens. That's a small change, so I doubt.
is this chaotic or?
It's not chaotic yet. It's the limit cycle with period 4. We can also
Okay.
see it down there. Wolfram alpha just tells me what I need to answer. But let's change it now to 3.54409. Oh, it's still period 4. Oh, limit cycle with period 4 that is loading, but now you can also see this is the cobweb diagram that I was telling you guys before. And this is sort of more, these are now 4 points. It's a little bit harder to see, but there are 4 points now on which the system oscillates between. And these 4 points, you can see them here, 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 and here. And that all the trajectories basically just go between these 4 points, and you go within this loop. Now, if you,
I'm sorry, I've gotta look at it later.
it's just harder to understand the cobweb diagrams a little bit?
Could you scroll back down?
Each one of the
actually?
points of the cobweb should be a different resulting point.
So these are these.
So basically, you keep moving. If you are at one of the points here, right?
That should be one
You
point
keep
on the cobweb,
moving and you
shouldn't it?
go back. You basically, this is, if you do the cobweb diagram, this is what you'll be doing. And you move between these 4 different points.
What are the 4 again?
The 4 different points
Are they
are the
here?
ones,
Here, here, and here.
well, you have to find the corresponding ones basically
They
on
have
the.
to be on the curve, right? So they have to
Yeah.
be this way.
So, well, the corresponding ones, you find them, so the xn, you find just by basically finding them what they are on the x-axis, these 4 points, right? So, so for example, this one here, this is almost 0.3, should correspond to this one. This one here, and then this one here should probably correspond to this one, and so on. So you have these 4 different points here, and maybe it's a little bit harder to understand the diagram. I didn't do a very good job explaining it, but if you then trace back these 4 points here, you'll find the same 4 points here, 1, 2, 3, 4, that the cycle is in. And this is a 4-point cycle, but if we increase our, let's say we now put 5.699. Okay, now we get a limit cycle with period 8. So now we come back to our initial points every 8 generations. Now we have 8 points that the system goes through before repeating. So this is a limit 8 cycle. If we increase our just a little bit, it's still 3.5, but it's basically the 100th decimal that changes. If we increase even more, so we're still here. So now if you look at this is the bifurcation diagram that I kind of kept hidden from you guys. So if we look at the bifurcation diagram, we have R on the x-axis, and we have sort of how on the y-axis we have the solutions of the system. So basically, it's really back to going back to what I was telling you guys about bifurcations. For very small r, we always go to 0. These are our fixed points here. So for r between 0 and 1, we always go here. For r between 1 and approximately 2 something, even 3, I think, for r strictly smaller than 3, we have this fixed point that changes location based on the value of r. For r larger than 3, we start having sort of these bifurcating fixed points. So you could either be in this point or in this point, right? You can see the fixed points here. Then we saw that we went through a period of 4 different fixed points. Then as we increase r even further, we go through a period, this limit 8 cycle of 8 different. So basically there are 8 points on the x-axis here. And very, very rapidly, as you increase r, it doesn't have to increase very much, but as you increase r past a threshold value, that is 3.5699,469, and so on. This is the limit cycle where you basically double each period. So it's called period doubling. So you go through cycles, 4-point cycles, you go 8-point cycles, 16-point cycles. So you double basically as you increase r through these points, you double all these points. So basically, the number of the points that you see here on the y-axis is doubled for different values of r. So now, if we put 3.9, yeah.
So I remember reading somewhere that there's some constant, some universal constant that tells you the difference between each bifurcation R value. So at each R value, at which a new bifurcation occurs, is there some ratio or some number?
I think there's a ratio. I don't know it right now, but there's definitely, there is a ratio, and you can actually find there is this R that is called R with like a little infinity at the bottom, after which the system becomes very chaotic. You can't predict. So if you go to R equals 3.9, for example, here, you go out of these cycles. So these cycles happen up until an R of a certain value. Past that value, you cannot predict. If you look now at our diagram, it's not periodic anymore. It's called chaotic in the sense that, well, it's aperiodic. Let's just call it aperiodic for now. But what is interesting is they call it chaotic because if you change the initial conditions, it's not the same trajectory anymore. We saw before, we change the same initial conditions, same R, you eventually fall into the same trajectory. Now, even if you go 0.51, the trajectory is, you don't go through the same points anymore. And it could be quite different. So past this here in the bottom, if you zoom in, it shows you this is R again, 3.83 here, and 4, and you sort of, it's very interesting that there are periods of chaos. So here there are some periods, 3.9 is the one we tested. This is where we are now, periods of chaos where the system just has this random behavior and it depends very strongly on initial conditions. But what is also very interesting, and we'll talk about more about this, is that there are also periods where the system starts being quite stable. Here it's again a period of 4 for R equals 3.85. So after a certain R infinity, it's back to being chaos or very, very period doubling or very stable behavior. So it's very interesting to see these bifurcations and to understand sort of that you can have such simple rules and yet behavior that you cannot predict. And that's what we're trying to talk more in this class also. But I also wanted to show you this graph. This is the discrete version of the logistic equation. But I wanted to show you guys, if you plot the logistic, if you look at the continuous version of the logistic equation, this is what you get. Can everyone see sort of this tiny little graph at the bottom? This is R equals 4, R equals 2.7, R equals 2.1, R1. For continuous time, the system behaves beautifully. It's very smooth. And that happens, and for very small r, you can also see that the discrete matches the continuous. So for r.1, r.0.05, it matches the continuous system. And I wanted to conclude here, but also talk a little bit about what this means. It means that you have to, why does it happen? First of all, it happens because in the discrete system, you have this carrying capacity, right? So you overshoot. Each time, population growth is based at what your population is at the beginning of the generation. So you only have that information, and then nothing sort of prevents you from going past the carrying capacity and you're being brought back. So that's why you see sort of these cycles happening, whereas the feedback in a continuous system is continuous. So you can never overshoot. You have this continuous feedback that sort of keeps you in check. So it's very important when you try to model system to think, first of all, what makes sense for me? Biologically, if I want to model the number of leaves in a tree and how that changes over time, it might make more sense to model it in a discrete version. Keep in mind that it's sometimes very much easier to deal with continuous equations mathematically, and we saw that the discrete version can actually a lot of the times give rise to very weird phenomena and behavior. But one general point is that behavior of discrete and continuous time models will be similar if the change that happens within a generation of discrete time is sufficiently small. So if there's only a small change within the time unit that we pick for discrete time, we have to pick a time unit. We want to model the number of leaves as it grows, like per day, per year, and so forth, right? So within our time unit, if the change that happens is sufficiently small, these two behaviors generally tend to sort of give the same dynamics. However, if at each generation, like it happens here, if R is big enough, you tend to overshoot. Your growth rate is too big, and so you tend to overshoot. If R is small, within generation you don't move as much. So your the change that happens for your variables is small enough because R is small. Your growth rate is small. So that's why it sort of approximates very well what happens in continuous time. So next time we'll talk a little bit. I'm sorry I kept you guys over time. Next time we'll talk more about chaos.